We're lucky if we even understand 4% of our universe today. Astronomy is a very humbling discipline.
This is wrong, or this is a huge discovery. And we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Through the vast darkness of space, galaxies appear as distant beacons, cosmic cities blazing with billions of stars. For generations, astronomers have sought to unlock their secrets, pushing technology to its limits to peer farther and farther back in time. Now, with humanity's most powerful space observatory, we stand on the brink of answering one of the universe's most profound questions. What were the very first galaxies like? Did they burst into brilliance soon after the universe began, or did they grow slowly, hidden by the mists of time? Today, thanks to the unprecedented power of the James Webb Space Telescope, we are closer than ever to unraveling the secrets of the universe's earliest epochs. But as it turns out, the cosmos is full of surprises, and even a few cosmic impostors. Astronomers around the world have set their sights on the so-called first light, those galaxies born in the universe's infancy, just a few 100 million years after the Big Bang. These objects, impossibly distant and shrouded in ancient darkness, hold the keys to understanding how everything we know, stars, planets, and even life itself, came to be. To find them, researchers use some of the most advanced telescopes ever built, peering back in time by capturing light that has traveled across billions of years. The James Webb Space Telescope, or JWST, is the most powerful tool yet for this cosmic archaeology. Orbiting far from Earth, its massive golden mirror and sophisticated infrared detectors are designed to reveal the faintest glimmers from the universe's dawn. With its launch, astronomers hope to identify the brightest, most massive galaxies from the first billion years, a time when the universe was still in its cosmic childhood. But as with any great detective story, the hunt for the first galaxies is filled with twists. In a groundbreaking study led by Bangjeng Tom Sun and Haojing Yan at the University of Missouri, astronomers set out to find these ancient beacons using a clever observational technique known as the dropout method. This approach targets galaxies that seem to vanish in certain wavelengths, specifically those whose blue light has been absorbed by intergalactic hydrogen, a signature of extreme distance and youth. The team pored over a treasure trove of data from JWST, focusing on 4 vast patches of sky. In total, their search covered an area roughly the size of the full moon as seen from Earth. Within these cosmic fields, they identified 300 exceptionally bright objects, potentially some of the universe's earliest and most luminous galaxies. If these candidates truly hailed from the first billion years, they would defy our current theories about how quickly galaxies can grow, shining with an intensity rarely seen in the young cosmos. But there's a catch. The universe is a master of disguise. In the images captured by JWST, both genuine early galaxies and much closer, older galaxies can appear strikingly similar, especially when dust clouds come into play. Light from the earliest galaxies is stretched, or redshifted, by the expansion of the universe, shifting it into the infrared part of the spectrum. But nearby galaxies, cloaked in clouds of cosmic dust, can also appear red as tiny particles scatter and absorb shorter wavelengths of light. To the eye of JWST, both types of galaxies can mimic each other almost perfectly. To separate the real ancient galaxies from these cosmic lookalikes, Sun and Yan's team combined the classic dropout technique with advanced light analysis tools. They examined each candidate's spectrum, essentially its fingerprint of light, and used 3 independent software methods to estimate how far away and how old each object truly was. Out of their sample of 300, 137 objects had enough mid-infrared data for a detailed study. This extra data, allowed for a much more precise determination of their distances. The results were astonishing. Of the 137 main candidates, about 2/3, roughly 93 objects, turned out to be impostors, relatively nearby galaxies whose redness was caused by dust, not distance. Only about 7% or 10 objects remained as likely genuine high redshift galaxies, born in the universe's earliest moments. The rest, a quarter of the sample, remained undecided, ambiguous in their cosmic identity. For the gold standard in cosmic distance, true spectroscopic confirmation, the team was able to analyze 10 objects in depth. 7 of these yielded reliable measurements. 6 were revealed to be much closer than they appeared, from a cosmic era about 3 billion years after the Big Bang. Only 1 object in the entire sample stood the test, a galaxy known as F115d Brati-Sears 062, shining from just 600 million years after the universe began. This lone survivor is extraordinary. Its ultraviolet brightness and mass place it among the most extreme galaxies ever discovered from such an early epoch. Yet, even this cosmic heavyweight fits within the boundaries of our current understanding of early galaxy formation. Its existence pushes the limits of what is possible, but does not yet break our theoretical models. The other candidates, if confirmed as truly ancient, could still challenge our ideas with their incredible luminosities and implied stellar masses. The implications of this study are profound. Even with the immense power of the James Webb Space Telescope, the universe has proved to be a trickster, hiding many of its secrets behind misleading signals. The brightest candidates, the ones that catch our attention most easily, are often impostors, their true nature revealed only with the most careful analysis. For astronomers hunting the first galaxies, this means the road ahead will be more challenging, requiring new techniques and even greater caution. But it also underscores just how special and rare the confirmed early galaxies truly are. Survivors from the dawn of time, beacons shining across the vast gulf of cosmic history. To truly understand how astronomers separate real ancient galaxies from impostors, we must dive into the innovative techniques driving today's cosmic archaeology. The James Webb Space Telescope, or JWST, stands at the center of this revolution. Its unprecedented sensitivity to infrared light allows it to peer further back in time than any telescope before it. But even with this extraordinary power, the challenge remains. How can we distinguish between galaxies that are genuinely ancient and those that simply masquerade as relics from the universe's earliest days? The answer lies in the art of galaxy hunting, a careful process that blends classic methods with cutting-edge technology. Researchers like Bangjeng Tom Sun and Hao Jingyan from the University of Missouri have turned to the dropout technique, a tried-and-true approach that identifies galaxies by the light they lack rather than the light they emit. Here's how it works. Light from the earliest galaxies is stretched or redshifted as it travels across the expanding universe. As a result, these galaxies seem to disappear or drop out from telescope images taken at shorter, bluer wavelengths. By systematically searching for objects that vanish in certain filters but glow brightly in others, astronomers can assemble a list of promising candidates for some of the universe's oldest galaxies. But as JWST's new data reveal, appearances can be deceiving. The team analyzed a remarkable sample of 300 extremely luminous objects, each selected because it seemed to fit the signature of a galaxy from the universe's first billion years. To refine their search, they focused on a main subset of 137 candidates that also had mid-infrared observations, critical for teasing apart the nature of these distant beacons. What they found was both enlightening and humbling. Of these 137, approximately 2/3, about 93 objects, were not the ancient fossils astronomers had hoped for. Instead, they were closer, older galaxies within our cosmic neighborhood, cleverly disguised by thick veils of cosmic dust. This dust absorbs and scatters blue light, making these galaxies appear deceptively red, mimicking the telltale sign of extreme distance. Only around 7%, or 10 objects, maintain their status as likely genuine early galaxies, while the remaining 25%, 34 objects, defied easy classification, their true nature still shrouded in mystery. To distinguish impostors from the real survivors of the dawn, the researchers combined 3 independent software tools to estimate the cosmic distances of each object, using the galaxy's light spectra as a roadmap. The gold standard for confirmation, however, is spectroscopic measurement, directly analyzing the light to determine its redshift and, therefore, its age and distance. Yet obtaining such measurements is painstaking and resource-intensive. In this study, only a handful, 7 objects, had reliable spectroscopic data. Of these, 6 were revealed as later galaxies, dating to about 3 billion years after the Big Bang. Just one, tucked among hundreds of candidates, stood the test as an authentic denizen of the infant universe. This extraordinary survivor, cataloged as F115D Bartseers 062, offers a glimpse into the universe as it existed just 600 million years after its fiery birth. Its intense ultraviolet brightness and sizable stellar mass place it among the most extreme galaxies known from such a remote epoch. While this discovery fits within the boundaries of current models for early galaxy formation, it also serves as a critical benchmark, an anchor point in our understanding of how the first galaxies ascended. The implications of these findings ripple across the field of cosmic archaeology. The high contamination rate among the brightest candidates, an estimated 67%, highlights a fundamental limitation in our search for the universe's primordial structures. Even JWST's powerful infrared eyes can be misled by the clever disguises of dusty, relatively nearby galaxies. This means that for every genuine ancient galaxy uncovered, many more are likely impostors, and only the most rigorous analyses, combining different wavelengths, advanced software, and the painstaking acquisition of spectroscopic data, can reveal the truth. Yet far from diminishing the importance of early galaxy discoveries, these results make the confirmed survivors all the more extraordinary. In a universe teeming with dusty lookalikes, true ancient galaxies become rare jewels, evidence of cosmic processes that shaped everything we see today. Each one we confirm is a witness to the dawn of structure, a beacon illuminating the chaotic, creative fires that forged the first stars and galaxies. The study also illustrates the limitations and challenges of even our most advanced instruments. The main sample was selected for brightness, meaning fainter early galaxies, perhaps more typical of the young universe, remain largely unexplored. The direct spectroscopic confirmation, vital for absolute certainty, could only be applied to a small fraction of candidates. As a result, while the brightest and most massive early galaxies are the easiest to spot, they may not represent the broader population of the universe's first light-bearers. Nonetheless, the methods and insights from this work are already shaping the strategies of future space missions. Astronomers now know they must be cautious when interpreting the brightest, reddest objects in their surveys. They're refining their techniques and seeking out new ways to separate genuine high redshift galaxies from impostors by combining data from multiple telescopes, leveraging advances in artificial intelligence, and designing new spectroscopic campaigns to probe deeper and with greater certainty. Behind the scenes, the study's success also reflects the collaborative spirit of modern astronomy. The analysis relied on public data from JWST's surveys, covering 4 blank regions of the sky that together span an area roughly equal to the full moon. Support came from major research grants and the efforts of scientists and engineers across institutions. It's a testament to the power of shared resources and open data, enabling discoveries that stretch our imagination to the very edge of time. With each new confirmed ancient galaxy, we peel back another layer of cosmic history. We glimpse the universe not as it is today, but as it was in its wild, youthful beginnings, a time when the first galaxies blazed into being amid darkness, and the story of everything we know was just beginning to unfold. As our quest continues, the lessons of JWST remind us the cosmos guards its secrets closely, but with ingenuity, patience, and relentless curiosity, humanity is learning how to unlock them. But even as we celebrate each new discovery from the James Webb Space Telescope, this latest study reminds us that the cosmos can also be a master of disguise. Out of the 300 exceptionally bright galaxy candidates that astronomers selected using the sophisticated dropout technique, only a tiny fraction, about 7%, may be true relics from the universe's earliest billion years. The rest, it turns out, are mostly cosmic masqueraders, galaxies much closer to us in space and time, whose dusty veils make them appear as if they belong to the ancient dawn. The challenge, as astronomers have found, lies in the deceptive power of interstellar dust. When we peer across light years and eons, both truly ancient galaxies and certain nearby dust-enshrouded galaxies can appear strikingly similar. The redness in their light, so crucial for identifying the universe's first galaxies, can arise either from the stretching of wavelengths over vast cosmic distances, or from dust grains scattering and absorbing starlight right here in our cosmic neighborhood. To even the most advanced infrared eyes of JWST, these impostors can be nearly indistinguishable. To separate the genuine ancient galaxies from their look-alike counterparts, the research team combined the classic dropout technique with cutting-edge light analysis. They meticulously sifted through data from 4 major survey fields, covering an area on the sky as large as the full moon. Only the brightest candidates were chosen, those whose luminosity, if truly ancient, would mark them as some of the most extreme galaxies ever seen from the dawn of time.